Lesson 2.3, Factorials and Permutations. Today's goal will be to understand what a factorial is and how to use it to solve permutation questions. First of all, what is combinatorics? Because our organized counting unit is really a unit about combinatorics. So, combinatorics is a branch of mathematics that deals with ideas and methods for counting. This seems like a simple task, but it can get very complicated. Consider counting how many possible license plates there are in Ontario, or how many 5-card hands are possible within a standard deck of cards. Often we can use organized counting methods like tree diagrams, lists, charts, and Venn diagrams to help us count the possibilities in a given situation. Other times, these methods can be too time-consuming, so we choose to rely on other counting methods like permutations, which we'll talk about in this lesson, or combinations, which we'll talk about soon, to perform these calculations. Permutations allow us to count the number of ways we can arrange a finite number of objects. Combinations allow us to count the number of ways we can select a number of items from a given set. What's important to understand here is that when we're dealing with permutations, we're counting the number of ways we can arrange. So the order actually is very important for permutations. However, with combinations, we're counting the number of ways we can select. So it doesn't matter the order when we deal with combinations, just how many different ways you can select. And this will become much more clear as we move through the course and as we move through different questions. But this video will strictly focus on permutations. Part A, factorials. Many counting and probability calculations involve multiplying a series of consecutive natural numbers, and we've actually seen this before over the last few lessons. So let's take a look at example number 1. 5 friends are posing for a photo that you are taking. If they stand next to one another, facing you, how many possible arrangements could you have? So here I've drawn the 5 possible positions for the seating arrangement. So here's seat 1, here's seat 2, here's seat 3, 4, and 5. And since there are 5 people posing, in seat 1, there are 5 different options of people who can sit there. And then once one person sits down, there's only 4 options. And then there's only 3 options, 2 options, and then the last person has to sit in seat number 5. And this is equal to 120. And we knew to multiply all these numbers together because we've already learned about the fundamental counting principle. But what if you had 15 friends posing for the picture, or 25 friends? You would probably not be inclined to multiply out the entire product of 25 times 24 times 23 all the way down to 2 times 1. Instead, you could use factorial notation to help you calculate this more easily. And that is 25 with a little exclamation point at the end. And what that is equal to is 25 times 24 times 23 all the way down to 2 times 1. And the reason this is helpful is because this little factorial symbol is actually on your calculators. So instead of typing all of this in, since we know that this is equal to that, you can just type into your calculator 25 factorial, and there should be a button that looks exactly like the exclamation point. So let's talk about factorial notation in general. For any natural number, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to 3 times 2 times 1, where the expression n exclamation mark is read as n factorial. So now let's take a look at example number 2, where we're going to evaluate each factorial expression. 5 factorial. I can either type into my calculator 5 times 4 times 3 times 2 times 1, or I can type in 5 factorial and I should get 120. Now we're going to skip a few and move down to D over here. I would like to bring your attention here because 10 factorial is equal to, of course, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And if we notice that this last part of 10 factorial is the exact same thing as this part of 5 factorial, we can, of course, just cancel that out, and then all we're left with is 10 times 9 times 8 times 7 times 6. Which is equal to 30,240. On your own for next class, complete B, C, and E. Now we're going to move on to part B, permutations. A permutation is a distinct arrangement of a certain number of items in a definite order. As you choose your first thing, you cannot re-choose that same thing, so your options have to be decreased by 1, which is of course why factorial notation begins to make a lot of sense. For permutations, the order in which things appear is important. In this class, we're going to talk about two main types of permutations, ones where we arrange all the items, and some where we don't arrange all the items. In situations when you are arranging all the items given, this is sometimes also called an arrangement. We're going to move on to example number 4. There are 10 songs on the Pink Floyd album, Dark Side of the Moon. If I play the album on shuffle using my iPod, how many different orders could the 10 songs be played without repetition? And this would be equal to 10 factorial, which is equal to 3,600,000, 28,800. Using the fundamental counting principle, the total number of ways of arranging all n distinct items is, of course, n times n minus 1 times n minus 2, all the way times 3 times 2 times 1. And of course, that can be written as n factorial, but we could also write that as npn or pnn. Therefore, 10 factorial is equal to 10p10, p1010, which is of course equal to 3,600,000, 28,800. Now you may be thinking right now that you're a bit overwhelmed because there's a lot that just happened, but what I want to make clear is that 10p10 or p1010 is really just another way of writing 10 factorial. It's just notation. It's not any new math. So what it's saying is I have 10 items and I'm arranging all 10 items in a permutation. Okay? And then over here, it's the exact same things. I have 10 items and I'm arranging all 10. And these two notations will become a little bit more evident and useful when we have a certain number of items, but we're not arranging all of them. So that's when we'd use these, but it's a good thing to get a hang of it now. And of course, if we're arranging all 10 items, that's the same as 10 factorial. Now we're going to take a look at example number 5. In how many ways can you arrange the letters of Langford? Since there are 8 letters and we want to arrange all 8 of the letters, we can write 8p8, which is equal to 8 factorial, which is equal to 40,320. What if L must be first and the D must be last? Well, if the L must be first and the D must be last, we're left with 6 different letters in between L and D with 6 different positions that we need to arrange. So that would be 6p6 equaling 6 factorial equaling 720. What if G must not be the 4th letter? Now, it's these type of questions that we really have to rely on logic to help us, because what I could do is go through each individual case where G was the 1st letter, G is the 2nd letter, the 3rd letter, not the 4th, but the 5th, the 6th, the 7th, and the 8th, and then total them all up together. Or I can take an indirect approach. So I know that if G must be the 4th letter, then there are 7 letters left, and I'm going to arrange all 7 letters, so that's equal to 7 factorial. which is equal to 5,040. And that's how many arrangements I can have when the G is the fourth letter. So if I want to find all the cases where G is not the fourth letter, what I'm going to do is I'm going to take all the possible cases, which is up here, and I'm going to subtract the cases where G is exactly the fourth letter. So that's 8 factorial minus 7 factorial, which is equal to 35,280. Now we're going to move on to part 2, where we are arranging R of the n items. So this is the second case where we're not necessarily arranging all of the items that were given. So what if we don't want to select all n items? We want to select a few R items at a time. We are looking at a scenario where we have n items and only R positions available to arrange them in. Now we're going to take a look at example 6. How many 4-letter arrangements can you make using the letters from the word potluck? First, we're going to attempt this question using logic. So I have 1, 2, 3, 4, 5, 6, 7 letters in the word potluck, and I have 1, 2, 3, 4-letter arrangements that I'm concerned about. So if I have 7 letters in the word potluck, the first space that I have here has 7 different letter options. And then once I use one of those letters for that spot, I'm of course left with only 6 letters left. And then when I use one of those letters, I have 5 letters left, and then I have 4 letters left. And so we know again by the fundamental counting principle, the way that we're going to get the arrangements is by multiplying these, and I should get 840. Now this example was fairly tangible because we were using small numbers like 7 letters and a 4-letter arrangement, so we were able to use logic to actually figure it out. However, if we were given much larger numbers, this would be much more difficult. So it's definitely very helpful if we can generalize what we did using logic into some sort of formula that we could use for the future. So the total number of ways of arranging R of the n items is n times n minus 1 times n minus 2, da 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 da, all the way until you get to R minus n plus 1. Now, why does that make sense? Let's take a look back at our potluck example. If I have n things, so in this case 7 things, and I want to arrange them into 4 specific slots, what I really have is just the first 4 terms of 7 factorial. Now how do I actually mathematically write out, hey, I want the first 4 terms of 7 factorial? Well, first you need to start with, of course, 7 factorial. Now we learned from our factorial practice earlier that when you have factorials over factorials, the bottom half often cancels out. So we want to cancel 3 other terms, because there would be 3 times 2 times 1 over here. So what we want to do is we want to can't have it over 3 factorial. So 7 factorial over 3 factorial is equal to our answer. And how do we get 3 factorial? Well, 7 minus 4 is equal to 3. So in general, if we move back down here, we can see that we have the total number of items on top, n factorial here, over n minus the number of spots we have, factorial. And so when it's fully written out in factorial notation, we have all of the factorial all the way up into 1 just before r. And that's what we have here. So when we want to make a general claim, down here at the bottom we have therefore. We can have n, p, r, where n is the number of items that you have, and r the number of slots that you want to put those items into. Or I can write this as p, n, comma, r, which is of course the same thing, just different notation, where n is equal to the total number of items, and r is equal to the number of slots that we want to arrange these items into, which by our formula we can write n factorial over n minus r factorial. And this formula is going to be super important, okay? That's where we're going to do a lot of evaluation, which is equal to n times n minus 1, dot, 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 all the way to n minus r plus 1. So continuing with our question 6, where we're dealing with the word potluck, so I'm just going to write that here so we can have a visual. What if we were concerned with making arrangements where we did not include vowels? So that's part B. So that means that O can't be used and U can't be used. So now we're only left with P, T, L, C, and K. So that's 1. And so since we only have 5 letters to deal with, and we actually still want to make a 4-letter arrangement, we have 5P4, which is equal to 5 factorial over 5 minus 4 factorial, which is equal to 5 factorial over 1 factorial, which is equal to just 5 factorial, which is equal to 120. Part C, what if you must include the letter C? Again, this is one of those questions where we really have to think and use our logic. So since there are 4 possible spots for the letters that we're arranging, C can be either in the first one, the second one, 1, 2, 3, 4, the third one, or of course the fourth one. And then we're going to use all the other letters to populate these other spaces here in our 4-letter arrangement. So in this first case over here, okay, we have 7 letters, and we have taken away one of the letters because that's C. So we have 6 letters, and we want to have 6 letters total, and we want to fill 3 spots. So it's 6P3. Now, over here, we actually have the same situation over here because we have 2 over here and then 1 spot over here, but there's still 3 spots altogether that we have to fill, and we have 6 letters still total because we still have the C taken, so this is 6P3. And then, of course, over here, all the empty letters are equal to 6P3, and then same with the bottom one, 6P3. So what you may notice by our additive counting principle that we've already talked about, when we have different cases, so this is case 1, this is 2, 3, 4, we have to add those up, so that is 6P3 plus 6P3 plus 6P3 plus 6P3, which is equal to 4 times 6P3, which is equal to 4 times 6 factorial over 6 minus 3 factorial, which is equal to, and since I don't have a lot of room, I'm going to evaluate this all at once, so it's equal to 480. On your own, complete question 7, and we will take up the answers in our next class. Be sure to bring your textbook to class because we will continue to work on questions from the textbook during class.